once again, introduce myself. My name is Max. I'm an officer here at CougarCS, and the lovely Jay Goldberg.
Even more lovely.
Yeah, so thank you guys for coming. Real quick, before we get into it, please sign in here, and I'll just go over kind of our roadmap for next week in terms of what's going on. So today we got some insights from computers. An Exxon Mobil info session up on it first. We also captain info session on April 2nd. Officer panel on April 3rd. So if you're interested in being officer or contributing more to the club, be sure to come.
You want to be a CougarCS officer? You want to be a CougarCS officer?
No.
Okay, just checking.
So yeah, without further ado, here's a small little slide on some things that we'll be discussing throughout this.
Okay, I didn't need to remember them.
Yeah,
You
well,
wrote them down for us.
Just in case.
these are just ideas. This could be an open forum about what we want to talk about.
So yeah, the conversation originally got started with the question, not a question, it was a complaint that one or the other or both of us was making, that CS curricula don't and haven't ever actually prepared CS students for life in the real world, not just to be, capable drones in a CS industry, but actually productive developers and deployers of software. So conversation about what doesn't the curriculum teach led into a much bigger conversation about, well, what would we want people to know? What do we as hiring managers, when that's part of our role, what do we want people to know, or what do we feel like we have to teach them if we're getting them fresh out of school? So that list of things are some really high-level topics that we can get into. The next to last one on the list is actually where the conversation started, because when I was a student here, did a couple of years co-op work for IBM in Florida. And when you do a co-op term, you get your grade based on not the work that you did at the company, but on the paper you write about it and turn in at the end of the year. And instead of writing about the work that I did, I just finessed that by telling them that I'd signed an NDA and couldn't talk about it anyway. But what I did talk about was what had really struck me about working at IBM was that their entire development methodology was structured around successive phases of testing. I was a junior in CS at University of Houston, which had the premier CS program in Texas at the time. And we didn't learn anything about testing. The closest we came to learning about testing was to prove the correctness of an algorithm theoretically, which really doesn't have anything to do with whether your code works or not. So I came away from that experience and graduated with my degree from here with a real understanding that there were things that industry cared about and was going to want me to care about that I wasn't getting from my CS degree, my studies, which isn't to say that my studies weren't incredibly worthwhile. This is one of the areas, one of the fields that I'm aware of where the stuff you learn in school actually shows up in your daily life, in your career. Any number of people get degrees that they never use. We use them. So I'm going to cede the floor to Jay to make whatever introductory remarks he wants, and then I'm going to turn it over to Max to actually shape the conversation in a way that he thinks is going to be useful to you guys.
So we're going to introduce ourselves a little bit. You saw my name was Jay there. We both graduated from computer science at U of H. So this is near and dear to our hearts. I have worked for 4 or 5 different companies throughout my career. Every single one of them has been a software company, not a bank or a computer company, just a company that develops software. So I have the small companies from 4 or 5 people to big companies like 5,000 people. So I have a pretty good experience about how different companies work with software development. I have been participating as a mentor at Code Red pretty much since its inception for many years. And this talk here comes from what we see happen at Code Red, where what the teams, how the teams are built, how they're interacting together, how they're just trying to decide what to do, how their development process goes. All those things aren't really taught in computer science. You're taught how to code, which is fine because that's what you need to do. But there's a lot of other stuff besides that. And that's what we saw what that was lacking from the classroom.
Yeah. That's actually where a bunch of the stuff, in fact, requirements definition and this coding and development priorities, those were very much a.
And this list was twice as long as this. We just had to cut it down. There's
lots.
If this thing happens to be successful, we will be back.
Yeah. I didn't actually introduce myself. Jay and I both graduated together and have worked together off and on for all the years since. First several jobs were together. Jay has always been in software. I have been in software development as one of his teammates a couple of times. Transitioned into consulting and deployment, doing applications deployment in industrial sites. Eventually made a brief decade-long foray into IT executive management, which was interesting and worthwhile for what I learned from it, but wasn't a phase of my career that I particularly enjoyed, and I don't do that now. But we've both been hiring managers. We've both been people evaluating new hires
And
recruits.
resumes.
What's that?
And resumes.
Oh, and resumes, and evaluating the work that people are doing. So, what else? Oh yeah, and now I'm back. I'm working now for a software development company, but I'm in a consulting role. I'm not writing low-level, distributed, replicated, ACID compliant database code.
I am.
Hey, and with any luck, he'll be using my database.
No, I'm actually still coding on a daily basis. So that's learned it here, love it, still do it. So how do we want to start this?
What I want to ask, what do you mean by requirements? What are those?
So, in the simplest, at their most basic, requirements are what it takes for a customer or client to accept what you wrote. That's it. The actual definition of a requirement is, did they accept it? If not, why not? What didn't it do that it was supposed to, or how wasn't it put together that they thought it was going to be? The thing about requirements definition, and the other word that goes on that, is elicitation. When you guys get an assignment,
That's requirement.
that's a requirement. We want you to write a subroutine that does this, that implements that. And as often as not, the requirements include, it must pass these tests. You have to demonstrate that, you can traverse your linked list backwards and forwards and handle the edge cases when you reach the end of the list, whatever. Most requirements are presented pretty simply. They read like they're cut and dried. They read like they're complete. They almost never are. And
No,
there's
never are.
they never. And there's a whole lot of things that are requirements that the people who are giving you requirements don't realize. There's a whole it's fundamental in problem solving in general, and in computer science and software development in particular. People will come to you and say, I have this problem and I want you to solve it. But what they tell you is, I have a problem, and they don't tell you what the problem is. They tell you what they think the solution looks like. I need you to write a routine that does X. I need an object that does Y and Z. That's not the problem they need solved. That's their notion of what a solution looks like to a problem they haven't explained to you yet. And because they are not analysts, they're not people who do that for a living, chances are they haven't thought the problem out really thoroughly, and they probably haven't come up with the ideal solution. So when you're a software designer, when you're a consultant, big part of the job is figuring out what the requirements really are. And that's why I use the term elicitation. You are eliciting requirements from people who don't realize they haven't given them to you. That, by the way, implies a whole other dimension of this job, which is being a really good communicator and reasonably tactful and diplomatic. Because when somebody tells you what they want, what they think they need, and you explain to them that they don't know what they're talking about, and can they please go back and work through it again like they're five, you have to find a way to ask that set of questions so that they don't get insulted and fire you on the spot. But the exercise of picking out what's the real problem and what are the characteristics of a solution that will be acceptable it's an art form, and we're happy to talk. And we could talk about just that for the next hour and a half if you felt like it. But I'm gonna let Jay comment on requirements.
So requirements in the software development life cycle are supposed to come first. And there's a kind of a loop in your workflow. Requirements come into the development team. Requirements are what, not how. Requirements are what do we need? What should it do? If you ever see a how it should do it, throw those away. Those are not requirements.
Yeah, that's somebody doing your design job for you.
Yes. So requirements are what do we need it to do? It goes to the development team. This is SDLC, Software Development Lifecycle. Goes to the development team. Development team goes over requirements and marks them in big red ink because they will not be complete. There will be so many edge cases that are not answered, and you can't really continue until you know all those edge cases. The worst answer I ever got about asking a question about an edge case was, it won't happen often.
It's one thing to say, well, what if this string of number ends with a negative? And they go, oh, no, that can't happen. Okay, if it can't happen, if you're insisting that it can't happen, it won't happen. If it happens, it's an error, and I can just quit. Cool.
Yes.
That's an easy case to handle.
But it won't happen often is not.
No, that means...
Anyway, so there'll be a loop between the people writing the requirements, which could be a customer, it could be product management if you're in a bigger company. You'll go back and forth, back and forth, back and forth. I wouldn't be surprised 10, 20 times before you are in a position that you can start working on a design for your software. How it's going to work. Not what it's going to do, but how it's going to do it. How it's going to do it should be written from that's a different discussion, but written from the bottom up. There's database design and there's service design and communication layers and API. But if you don't know what the product's supposed to do down, like say 90%, because you're never going to get to 100%. If you don't get down to about 90% of what this is supposed to do, you shouldn't even start. And I get in trouble all the time at work for starting to write code without complete requirements. I get my dev manager hits me all the time up with that, because I'll just start writing code and then I'll come up with a problem that wasn't answering the requirements. And now I got to go back to product management and then I have to rewrite stuff.
And where that becomes really expensive is when the requirements that you've gotten and all the discussions you've had so far rest on some unstated assumptions that the requirements authors have made and not recognized, and that you don't even know were open to question.
We have an assumptions section in our requirements doc.
and when they tell you X, Y, and Z, and you go build something that absolutely it X's and it Y's and it Z's, and then they go, oh wait, you haven't handled this case. Wait, what do you mean this case? That's a W. Nowhere in the spec, but once you discover that W is part of the, oh well, hell, now my whole design is based on a super simplified understanding of what's going on here, and it's not going to be flexible enough or versatile enough to handle what are clearly going to be a whole bunch of edge cases or other things that are going to come up. It's like, You need to take an input and blah, blah, blah. And you go, oh, cool. All right, then. Oh, we didn't tell you after it's half written. That's for an input, but there can be any number of inputs.
So there have been attempts over the years to templatize requirements writing, store into stories, cases.
Yeah.
You can do that. Every software development product is different. They don't all fit into the same buckets. So a requirements doc could be written from scratch. It could be written from a template, but they're all unique and they're all incomplete.
True.
Wait, the assignments you get here in computer science, 1-2 pages of requirements, usually they are very complete because they've been developed over years of questions of students asking questions about the requirements, asking questions about the assignment you got, and then and if the teacher's good enough, they'll update the assignment to answer those questions. So when we were here at school, some of the assignments we got were probably a decade old and were tweaked for 10 years. So there's no questions left. But you don't have that kind of time.
Right.
What kind of questions to get a concrete family customer?
So I was gonna observe, and this reasonable lead into an answer to that is that different kinds of applications you talk about differently. A user-facing something that the UI is an important part of it, that it's meant to make a user's life easier. That's going to be one kind of application. Where Jay and I started out in industry, we were building software frameworks to create industrial control system applications on. Basically, we were automating factories, but we were writing some generic software tools for doing that. And when you go to automate a factory, a lot of the requirements are in fact very cut and dried. You need to be able to command this device with this particular command, and the range for values of that command are very specific, and this and that can't both be running at the same time. So you're going to get a whole pile of those. And then you kind of assemble that picture in your head, and what you're looking for are what Jay called edge cases. They're the, okay, that's the perfect flow. That's when everything's working. What happens if? And then you start asking questions around, and this is for
what
very
happens
simple.
if?
Yeah, that's a question. What happens if? And you, as somebody who knows how software works, somebody who knows how logic flows, well, I have to make a decision at that point. You've told me I get done with this, and it either goes here or here, but that's based on a condition. What if
I can guarantee that the initial set of any requirements you get, guaranteed, will not cover the bad path.
Right.
The customer or the product manager knows what they want the product to do, but they never, and they say, here's what it looks like, here's what it should do. But they never, ever, ever cover errors. There's always errors.
Yeah.
And when something goes wrong, the requirements will never, ever have that. So that's one of the first things that you ask is what happens when it doesn't work?
And then you get to point out all the many, many, many places they didn't think about where a thing might not work. And then they don't know the answers, by the way.
They don't.
When you ask, what happens if I'm supposed to be rolling over a log file and I close the log file and I go to open a new one and I can't? What then? What do you mean, what then? How does that happen? It doesn't matter. It can happen. Let us think about that. Going back and figuring out how they want to handle error conditions is a big part of requirements definition, because you have to know how. I mean, you're not allowed to just core dump every time something happens that they didn't anticipate.
You don't know what core dump is.
You can't, throw a trace log? You gotta change it. Once upon a time, when your program hit an error that it didn't know what to do with, it would just stop and it would write to disk the current state of all of its registers and memory and everything else, and exit, and you had to go look at this and figure out, what was the state of the system when it stopped? What did it think it was trying to do? So, sorry, I haven't actually had to pick apart a core dump in many years, but
How do you get real requirements that are different from what the customer is?
by the way, there is another variant path that you can go explore when you're doing requirements definition with a customer. Jay described, they know what they want it to look like when you do it right. Well, they have a notion of what doing it right looks like, and especially in something that involves a number of steps, they're going to assume that, well, everybody thinks about the problem the way they do, and they're going to do the thing. I can almost guarantee that the first online shopping cart that anybody ever wrote was written so that people went to a product, added it to the shopping cart, added something to the shopping cart, ... They finally went to the shopping cart and checked out. And nobody asked until it was already built, what happens if they navigate away from the shopping cart and try to add something new? I'll bet the first shopping cart crashed when that happened, because that wasn't the use case that anybody was thinking about.
What happens when they want to change how many of the item they want to? All those things were never probably in the first requirements that you have to ask.
And the reason, by the way, there's a whole other topic on naming. They called it a shopping cart. And the first time somebody put a shopping cart online, the only reference they had for that was, well, how do you use a shopping cart in the real world? And the answer is you go up and down the aisles, you fill up the shopping cart, and then you go to the checkout line. Nobody ever goes to the checkout line and says, how many bags is this going to take to fill up? And you know what? I need to go back and put some stuff on the shelves. Or, oh, I have more room in my car than that. Let me go back and find some more stuff. Because the metaphors people use for talking about their requirements, for talking about what they're doing, those metaphors shape how they think about things. And they will build in the electronic world things that mimic their experience in the real world, even though those constraints don't necessarily really exist.
So if you have a requirements that has a picture of an input page, a screen, could be an app on a phone, could be a website, and they want input. Some requirements will be detailed enough to say this needs to be a text string, this needs to be a pull down with these values. Many will not.
Yeah.
But then there will never be, and you have to ask for them, validations on all the fields. This has to be a number. Can it be negative? Can it be a too big, too small?
Yeah.
If it's a string, how long can it be? All these things need to be part of the requirements, because if you have a limit of 3 characters on an input string, your UI needs to be able to limit that, and that's part of coding. And if we don't have that in the requirements, the customer is going to put in 50 characters, because QE will do that.
Right.
QE will try to break it.
You guys live in a world where a lot of what he's talking about has been done and has become part of the state of practice, right? I don't need a character string with some special numbers and a few dashes. I need a phone number, and there are some well-developed validations for, say, phone number. But maybe not. There's country codes, and there's phone numbers of different lengths, and there's phone numbers with and without extensions, and there's all kinds of things that might make up a phone number. So you want to know, what are you going to do with it? If the phone number is only ever going to be something a human reads, you don't have to do any validation on it at all. It can just be a string. If it's going to be something that gets auto-dialed, you're going to, okay, that's interesting. What are the constraints that the auto-dialer is going to place on its inputs? That sort of thing. And so the validation rules for data that goes in, if any of you are database students, or if you guys are doing relational database design, this is a value, but is it a foreign key reference? Does that thing have to already exist? Or can I put in a placeholder and fill it in later when the thing gets created, because we're doing something in a transaction or we're cascading something? So figuring out what your inputs are is a whole exercise unto itself. And by the way, the same thing is true for outputs. Oh, I need you to write a report. Okay. Who's going to read it? What's it got to have in it? Oh, are there two versions of this report and one of them needs to be redacted? Okay. Which of these fields might have data that I shouldn't show to everybody, and how can I tell the difference? Lots of stuff like that.
So you could say that the requirement stage is a very important part of
It never stops. No.
It's an ongoing.
Jay was talking about the software development lifecycle that everybody learns first is waterfall. Right?
I hope you guys learned that, SDLC.
You do, right? They're teaching a software development lifecycle. Show of hands? Yeah, good. So the first one, the first flavor is waterfall. It's the oldest, and it mirrors the industrial age, right? When you're going to go build a factory, you don't start building a factory until you have a complete parts list and you know where everything's going to go. And once you start building, you don't make changes to the design without a really, really good reason. And so there is that model of building things. They called this software engineering, and that metaphor implied lots of things about how software development got done. They didn't call it software artistry when they started doing it. They were engineers, so they did things the way engineers did things. There are a number of SDLCs now, and pretty much all of them after waterfall are some flavor of iterative. And in the real world, even waterfall is iterative, right? You get requirements, you start working on design, you figure out your requirements suck and your design's bad. So you go back and you do the requirements again, and you slip your schedule and you get in trouble and you go over budget. But you keep doing this because it's more important that you get it right than that you build something and deploy it and it doesn't do what it needs to. That said, requirements keep making themselves apparent all the way through the system. And some of them will simply get logged as, okay, that's going to be a requirement for phase 2 or version 1 point whatever. A lot of systems, particularly sophisticated, complex systems, people have an idea of what they're for and how they're going to use them. And then once they get built, they find a life of their own. They get used in ways that are different from how they were initially intended or imagined. Or once they've made your life that much easier, it becomes clear how much easier it could be if only it did this and this. So requirements will keep coming up. Hopefully none of them breaking requirements once you've got far enough down the line. But you don't ever want to stop collecting requirements. And as they become apparent, you want to collect them and log them, because there will be another document you produce 6 months down the road that says, I'm proposing a phase 2 development where you're going to pay me a whole lot of money to build these 6 things that we have discovered we really need in this system. And you find a way to say that doesn't imply they were dumb for not having thought of it first.
I agree.
Jay agrees. Okay.
So,
Anything else you want to answer that question with?
No, I'm
right.
just sitting here thinking about code red.
Oh, let's talk about that. Can you go back a slide? Just, I want to throw up that list, because one of those is this one here, coding and development priorities. Because this is a thing we talked about in Code Red when Jay was thinking about Code Red. This is the very first thing I thought of. We learned a long time ago, and we had drilled into us, not at school. The priorities in school were a little different. Once we got into the world, the priorities were make it work. That absolutely fundamental requirement for a piece of software. If it doesn't do what it's supposed to do, you do not have a solution. You've got a body of work. It's like having a manuscript that nobody will publish, right? So make it work is fundamental. And whatever hoops you jump through, whatever shortcuts you make, whatever kludges you throw into the system, that's all part of the learning process. What does it take to make this work? Then you make it pretty. You go back and you find all those kludges and you figure out what's the right way to do that. What's the elegant, what's the graceful way? What's the way that actually uses a piece of software you've already got instead of one that you threw together because you didn't know what the library had in it. But make it work, then make it pretty. That is, make it kind of publication worthy, make it so that somebody's willing to sit in front of it and use it. And then last, not least important, just last in the list, is make it elegant. And by elegant, I tend to mean things like well-documented, maintainable, prettily factored so that maintaining it over time is easy. Wait, we have a coding standard? I should probably go and make sure that all of my variable names and decorations and the rest of that look like
Most
they're
software
supposed to.
companies will have coding standards. Who likes to document their code?
Nobody. That's
Who's told that you should document your code?
whoever got told there should be a line of document for every line of code.
That's wrong.
That is such nonsense.
When I was in school like you guys, I hated documenting my code. Over the last few decades of coding, I understand now.
I challenge you guys. Any one of you go back and try to modify a piece of code, a piece of a significant chunk of code, not a trivial exercise, but go back a year after you wrote something and see how long it takes you to wrap your head around, what was I doing here? How did I think this was going to work? Why is this loop here? Documenting your code is signposts. It's explanation. It's easier to write code documentation if you're bragging. If you're proud of this thing that you just did and you want everybody, all these other brilliant coders to understand it. Because that's what it's for. It's to make this stuff easier to understand later, even to you.
And I understand why in school it's annoying and seems a waste of time. And in some ways it is, because this code that you're writing in school isn't ever going to be seen or used again.
Right.
But it's a good habit.
And that you don't have to explain it to the only other people who are reading it, because they've seen it 150 times every semester for the last 5 or 6 years, because it's the example of code that they use. Yeah, documenting code in school is kind of pointless. But documenting code in the real world is terrifically important, and you'll discover that yourselves. Just don't wait too long.
Let's see, coding development. So there is this term called MVP. You all heard MVP, but not what we're talking about. And it stands for, in this case, minimum viable product. And with the schedules that the real world has for coming up with software, if you want to show something to a client as quickly as possible, you get it done in whatever way you can put wire together and put it together and come up with your MVP, minimum viable product, and just cross your fingers that your development manager will let you do it right the next time. Because then they'll just say, hey, it works, ship it. No.
Right. So this make it work first before anything else, and the minimum viable product, these both tie into the thing that we observed at this last Code Red.
Yes.
Jay's invited me a couple of times. This last time was particularly interesting.
So I work for PROS. Who was at Code Red? Good, nice, a lot of you. All right, so PROS had the assignment of the natural language flight request. And there were some really nice results that we saw. But as we walked around,
especially really early in the competition,
early in the first day, there was a lot of teams trying to design a UI.
And concerned about very UI things.
Yeah, where should the buttons go?
Having team meetings about size and shape of button. What kind of menus are we going to use? Do we need a boredom bar?
Go back to the requirements. The requirements had nothing about a UI. So the minimum viable product for that assignment, in my mind, maybe not in everybody's mind, but in my mind would have been a command line. You type in my request, hit enter, and it does what it does, and it spits back an answer.
I had an even more minimal viable product, because Jay's answer is an integrated solution. There were actually 3 things specified in that challenge. Take a natural language input, submit the relevant data from that to an online API, and take the results of that API query and convert it back to natural language. Well, for me, that was 3 distinct steps. So if I had 3 different command line programs, one where I could type this in and it would spit out, here are the relevant bits of data. And in the second, I had a command line that would let me submit those data in whatever funky format that the API required and get back an answer, and then submit that answer as a third step. I would have been happy to accept a team of 3 people, each of whom implemented one of those pieces, and that if you did the thing that they said in the order they said you needed to do it, and you got the answer that PROS was looking for, I've gone, okay, now all you need to do is integrate that, tie it together, stick it behind a faceplate. But everybody was starting in the opposite direction. That's then, right. So yeah, we came away from that little exercise with this kind of new appreciation for, among other things, the state of the software world that people have grown up in. We have the advantage that we grew up in a world that didn't have a whole lot of software in it, certainly not a lot of software that people interacted with. And y'all have grown up in a world where pretty much all software sits behind some sort of app, some sort of user interface, reactive, mobile, capable, always connected app. And so when somebody asks you guys to write a piece of software, that's what you're thinking of. Obviously, they're going to want
our guess about why teams started to design a UI first.
Right.
That's what we guess. That's what we're guessing.
Right.
Because you guys grew up with UIs.
Right. Well, that and the fact that there was an assumption about the requirements. You know, it was described as this allows users to, and immediately you go to, oh, well, users, they're going to be on a website. They're going to do this in a web-capable environment. And you're not wrong. Ultimately, that's where that would go. But that wasn't explicitly part of the assignment. And what they were looking for was, as CS students, do you guys know how to do this sort of data handling, this sort of transformation, et cetera? So it was an interesting exercise. And we only bring this up to emphasize that those assumptions about what's called for, not just on the part of the clients asking for something. It's easy to make assumptions based on your own experience with the software that you've used and built.
Can you talk about a little bit the initial requirements? How you approach starting the house?
I'm going to let Jay start.
Okay, so there's lots of methodologies for designing software. I've done many of them over the years. Lately, the idea of software is microservices. Who knows about microservices? Anybody? Thank you. Back in the back.
Give a brief definition.
So software, even in not microservice architecture, lots of pieces talk to each other. In a microservice architecture, you can separate those pieces into separate services, and then the services will talk to each other, and then you can distribute them across a network or the world. And
can I throw in a...
Sure, go ahead.
What he's describing is, it's I think worthwhile to think about this in a historical context. Once upon a time, a piece of software was a thing unto itself. It ran on a box and it did what it did. And you fed it stuff and it spit stuff out. The only moving parts there, the only different pieces that had to collaborate were the functions and subroutines within software. And then the coordination of those different things was the main, right? Then they figured out multiprocessing, and you end up with splitting things into multiple programs, and some programs ask for things and some programs do them when you ask them to. So you end up with things like client-server architecture, and then you invent networks and you get to distribute these clients and servers all over the place. And now you live in a world where we're writing programs that talk to one another. And now an API isn't just a library that you link that will do things for you, but inside your little monolithic program. You can talk to a program over there and ask it to do something for you and hand you back an answer. And as this idea keeps evolving, as you split things apart and give them jobs to do of their own, and you define interfaces between them, you end up with, now I've got this layer of very specifically focused question answering routines that live out in the world that you can connect to and ask questions and they'll give you answers. Those little bits of code out there that make up an API layer that you don't link to, you just access, typically sitting in front of data stores that somebody somewhere is managing for everybody's benefit. This is what microservices look like. And there's
So microservices enforce a concept that I learned over the years, which is, I don't think it's taught, is layering your software. Nobody? Okay. Layering your software. So the software will have a database, right? Most software has databases. You have to have persistence layer. That means you have to have a piece of your code that talks to the database. Then you have your logic. What is your program doing? That's another layer, your business logic layer.
But it's a layer because you've separated it out.
Yes.
You've separated it out because when you wrote it the first time, you had logic that needed data and it went down to the database and got it.
Yeah, do not do that.
And then it did other stuff and then it went to the database again and got stuff.
Do not do that.
And then somebody said, we don't want to use Foxbase or Xbase or whatever. We want to use this other database. And swapping out a database meant you had to go through and look at every line of your code and find all the places that you reached into a database. And somebody says, you know what? We're going to refactor all of this database access code out and we're going to put it in a library of its own. And we're going to make it the same library interface for all the databases that we might swap out. And that's where this layering comes from. This is refactoring or factoring out of software that you want to be able to maintain separately or swap out as interchangeable components. So
and that's exactly why you layer your code. You have your database layer, you have your business logic layer. Most likely the UI is up here and you have some kind of interpretation layer that interprets the UI input into some class or object structure that gets fed into the business logic. So if you have layer separation of all your software, then you can slide in a new database, slide in some new business logic, slide in a new UI, as long as they are all separated. You can do this inside of a single monolithic program that you write in one big, if you're a Java person, one big jar file. It's harder to do in one big jar file because you have access to all these other pieces of code that are there. You can jump right from the UI layer into the database layer.
and it's so tempting just to go do the easy thing.
It's very tempting to do that when you are in one big program, and it will work. Separating those pieces into microservices.
And you're allowed to do it here.
Yes,
under
you can make it work. Separating those layers into microservices prevent you from being able to do that, because each microservice that you create will have a specific API. I know a lot of people don't know what API is.
You guys can
We
show
figured
hands
that out
API.
during Code Red.
Yeah. API stands, I mean, it's super simple and it's been around since they invented subroutines, right?
Yeah.
An API is just an application programming interface and it defines all of the ways that you can call a thing, all the ways you can talk
So
to it.
if your database service is separated out and it has a specific list of API calls to get and put data into it, and then your business logic has to use those communication lanes to your database service, then it's easy to replace this one with another one that just uses the same API, and boom, you're in a new database. Doing that in a monolithic program is very, I wouldn't say difficult, but it's tedious because you have access to too much information. If you separate them out, here's my UI over here, it talks over a network protocol to your business logic. The business logic talks the network protocol to the database. All separate, they make it much easier to replace.
So encapsulated, that's part one of the
Encapsulation,
answer.
data encapsulation,
Right.
yeah.
Well, part one of the answer to best practices is separation of concerns, which is where the layering comes from.
Yes.
Have you guys learned, has anybody ever encountered MVC or model view controller as a framework, a structure? Okay. So
Don't like it.
that is a very specific and interestingly arbitrary separation of concerns, right? The model is the closest useful piece to this, which is I need to store it somewhere. Somewhere I need to have the ability to store, to fetch and put the thing that I'm talking about or the collection of things that I'm talking about. And then how somebody might want to look at it and what I want to be able to do to it are separate things. That, like I said, it's separation of concerns. That one's an odd one, and it's not actually how I design software particularly.
Yeah, anytime somebody comes up with a pattern like that, other people try to pigeonhole all software into it, and it doesn't work that way.
Right. Almost any pattern that somebody comes up with and talks to you about is a really good idea for some subset of the problems in the world. But, hammers and nails. So people who learn one or two patterns are going to use them for everything, even if they may not be the best choice. Interestingly, may not be the best choice technologically. On the other hand, if you must implement a project with this programmer, and this programmer only knows how to do two things, this project is going to get built with one of those two things, and that's one of those trade-off decisions you get to make. People program in the languages they know. There might be a better language for doing a project in, but is it worth learning a whole new language in which you then will not be expert just to build a project? Maybe, maybe not. So there's a whole conversation around trade-offs up there somewhere. Oh yeah, design choices. We make choices about stuff all the time. Do I use this library, this mechanism or that, this model or that, this pattern or that? Even do I assign it to this team or that one? And every choice you make, literally every choice you make that's an either or an either or is essentially an engineering trade-off. You are trying to maximize the return on one axis and you're having to relax your constraints on some others, and paying close attention to that dynamic, knowing what it is that you're trying to maximize or minimize, and knowing what it is that you are allowing that to cost you is part of the art and discipline of software design and development. That was an aside, by the way. That wasn't an answer to the best practice.
Separation of concerns was harder back in the day. With the advent of object-oriented programming, it made it easier because you can actually separate your concerns in an object. We didn't have that when we were going here. There was no such thing as object-oriented coding.
There was not.
It does allow you to say, okay, here's my database object, and anything that, and you can make it private. If I'm a Java programmer right now, so there's ways of making things isolated so you can't dig into the object. You can only look at it from outside. So you can make your database object, you can make your business logic object, you can make your data transformation object, and they can all talk to each other, and then easily become microservices in and of themselves. But data separation, I can't say enough how important that is. I have spent too much time separating code after it was written that was too. I'm not sure if you've heard the term spaghetti code, but
Apparently they have.
Apparently they have. If they're too intertangled, that's a sign of poor design, because this has to talk to here. No, it shouldn't talk there. And then you end up with a mess.
By the way, untangling spaghetti is part of the make it elegant piece, because spaghetti can work. Really difficult to maintain, won't survive long in the world without being papered over repeatedly or replaced. But spaghetti can work. Once it works, document it at least. Point out where you know you've made interesting design choices for the sake of getting something done by next week. And then ultimately, when you get a chance, you go back and you refactor that. Also, Jay said something a minute ago that reminded me of something I just wanted to say out loud. Also, not part of the answer to this question, but we were already professionals in industry when object-oriented as a concept got developed and standardized. We remember when there were 3 schools of thought about what object-oriented really meant and what that looked like, and eventually Butcher and Rumbaugh and what's his name all got together and they agreed, okay, after a decade of this fight, we're gonna agree on what's object-oriented. By the time that happened, we were already doing that kind of work. We didn't have languages that supported it, but the notion that an object is a thing that contains its own state, its own data, manages its own behavior, and presents an outside shell to the rest of the world to interact with. We were doing that, and we were doing that with all kinds of tools not really designed to support it, but we were doing it and doing it successfully. We also were around before Agile development was a thing, even before Agile development had got a name or had accreted the various techniques that came to be called Agile. But we were doing a bunch of those things. I think we invented pairs programming, or at least
No, we didn't.
at least we were the only people we knew doing it, because it wasn't how people programmed, or at least not how. My point here is this: if you guys are in this for the long haul, if you are going to be professionals and spend your career in software, a lot of the things that are fixed and given in your world today are going to change. So try not to be too married to the way things are, the way that you think they are, and conversely, recognize that the fundamentals don't change. The separation of concerns thing, we used to factor by turning code we use more than once into a subroutine. That was the first factoring we learned. Oh, if I do this 6 times in my program, I should probably make a subroutine out of it and call it. Oh, here's a thing that I read, and I have to be able to write a whatever out to disk. Why don't I make a library for that? I need to access this in a database. Why don't I make that a client server call? This stuff keeps happening. And the separation of concerns, how do you refactor the solution to a problem? That's going to continue to evolve. The issue of trade-offs is going to always be at the core of what you do, but what you're trading off, what's expensive and needs to be conserved versus what you're willing to allow to flex, those things are going to change. They've changed for us. When we got into software, disks were slow and memory was expensive. So you did everything you could to make your data structures as compact as possible. And all right, so what if it took your program 7 minutes to run? You only needed 16K of memory, and you could fit it all into a 16K diskette, right? That's fine. That's not the limiting factor anymore. Nobody needs to conserve disk space. You conserve what's expensive, and you spend freely what's cheap. And now, not just memory and disks are cheap, whole servers are cheap. You can spin up a VM in the cloud in no time, use it for how long you need it, spin it back down. So you will be making those trade-off choices all through your career. And one day you will fondly remember when, it was whatever it is that you're conserving now. Shaving 27 milliseconds off of a query response. That's going to be awesome. But no, what you're trading on, what your trade-off decisions are 15 years from now, I can't begin to imagine. and I suspect you can't either.
Because we couldn't imagine
I don't know.
what the software industry is like today when we were in school.
Wouldn't have imagined this just 20 years ago, and school was twice that ago. Of?
Like the trade-off, like current day.
Oh, sure, Jay, you're doing software development. What are you trading off at the moment?
Speed
Okay.
for
And not just speed, but
disk,
speedy response to a user request, because that's where speed.
memory.
Yeah.
So memory's cheap. So I happen to be one of our microservices that I work on a daily basis is a service that has
Good
to
question.
respond with service responds with data, and it's a very complex lookup. And the initial cut of this piece of software had a database with everything in it, and the query came in and it asked the database, and the database went, okay, here's your answer, and then it sent it back. Not fast enough. Back in the day, that was it. You had no other choices. Today, memory's cheap. So we literally read the entire database into memory, sort it, filter it, and keep it in a big cache. Requests come in, boom, answer goes out. So we sacrificed memory for speed.
Yep.
That will cost the customer because they have to buy more memory. There was no such choices back then.
Right.
You couldn't put enough memory in a machine to do that.
And if you ask the customer, would you rather buy memory or lose customers because they're not getting answers fast enough?
Yes.
They will spend on the memory. Another example, I'm working in the database industry now, and in particular, I'm working for a company that's convincing their customers to move from whatever database they're on to our database. So we're doing migrations. Database migration is, in principle, it's really simple. You take a backup of this database, you stand up your new platform, you import, and then you point all of your customers to all of your programs that look up data, you point them over to here. The problem is backing up, restoring, means that your system is down for however long that takes. Because if I'm backing it up and this is what the database is going to look like when I bring up the new system, no work can be done in that database in the meantime. Well, downtime, not really acceptable. If you are in business online and your customers expect for things to keep working even while you're doing stuff, then that database migration has to be seamless. And figuring out how do I get all the data from there over to here and let that database keep working and keep this one up to date with changes made over there, and ultimately repoint all of my client software from there to here seamlessly so that nobody notices and there isn't any change in responsiveness. That's an enormous investment in tooling, in additional infrastructure, in complexity, in programmer hours, because now what we have to do is go, well, all right, I'm going to export that database, but I'm going to keep using it. And I'm going to timestamp when the data came out of the database that I'm seeding this one with. And then I'm going to load up this system. And now I need a whole new tool that's going to pipe all the changes that have taken place since time X back then. And I'm going to feed all those changes over here. And I'm going to let them get caught up. And at some point, when they're completely caught up, I'm going to
What's the trade-off?
The trade-off is the enormous amount of time, energy, work, and additional programming and infrastructure that it took just to keep the system from being down for 4 minutes while we made this shift. And that's actually when we do a migration consultation, the very first question we ask is, what's your tolerance for downtime? And more, the answer is, not if we can possibly help it. So you're talking about spending a great deal more, making things a lot more complicated, and having a whole bunch of people working to keep all those parts moving, just so that this simple act of changing out the database, this separation of concerns that should have made it trivially simple, is exercisable in the real world.
And so, by the way, that's another thing that didn't exist 10 years ago, is DevOps. DevOps is a fairly new computer science industry that we have teams that are at PROS, where I work at PROS. We have teams that do DevOps because it is a new thing that you don't have to learn. Other people can learn it, and you just use them.
Yeah.
So how many servers do you think Amazon has?
Amazon doesn't know, so any number you give is fine.
Amazon.com. How many servers they have? 1? 2?
One.
Okay,
We
so
call it the Earth.
Let's say they have 1,000 servers. Does Amazon change their software ever?
All
Yes.
the damn time.
Yes, they do. They have 1,000 servers with their software running on it. They make a fix. Now 1,000 servers have to be updated. That's not a manual process. That has to be some kind of DevOps process. Another problem that is easily foreseeable is that the new software has new APIs and new database accesses. So what do you do first? You upgrade your database? You upgrade the software? I don't know. Well, let's say you do the database first, because you have to have, so the new software is talking to the database in a new way. So you upgrade so let's upgrade the database first. Wait a minute, you have old software running. How can the old software talk to the new database?
I don't think it can.
Well, so what I'm trying to get at here is everything has to be backwards compatible. So when you do upgrade the database or the software, they can still talk to each other. And then you just slowly upgrade everything. And it becomes seamless, but there's your trade-off, is like you have to be able to, you can't just code willy-nilly. Oh, I'll just change the interface. No, it has to be backwards compatible with the old interface. And we never had to deal with that before.
No. I mean, at least when we were much younger, swapping out software was shut it down, install something new, spin it back up. And that was true as recently, even in standard practice, as recently as 10 or 15 years ago. I was running an IT department for an engineering firm, and when we needed to swap out a service, if there was, if we were going to even upgrade in any significant way, for instance, the mail server or the authentication layer, we would shut it down. We would make whatever changes were necessary. We would bring it back up. And that was a scheduled outage, and that was, maintenance window. You don't hear about maintenance windows nearly as much anymore because so much of what runs needs to just keep running. I want to come up with another couple good examples of trade-offs because they're the most important thing.
Well, no.
No?
I'd rather talk about testing. We'll never get to teamwork today, but we'll talk about testing.
Fair.
I know we just made note of Amazon having 1,000 servers.
They have more.
Don't. They have 3 million.
They have more.
Trillion. Yeah, it's ridiculous.
How are these servers affecting?
Oh, that's a story.
Show of hands, who wants us to talk about the cloud now?
Oh
Apparently,
boy. Let's talk about the cloud.
That's the next conversation. All right.
Let's start with mainframes.
Right. The cloud evolved to what it is, and you need to know where it came from.
So mainframes were the first computers, before laptops, before desktops, mainframes. And they were big. And you heard the stories about filling up a room. They're not lying. This room would hold a computer. They were not very fast, did not have many storage, but what they could do was a lot of things at the same time. They were very, very multi-threaded and multitask. I remember working on a mainframe. We had a wall of modems that people were calling in. and all using the same machine at the same time. Time slicing out and essentially buying server time on the big machine, buying the big IBM machine. They're buying pieces of the computer at rates per minute or per hour.
By the way, remember that. And
Yeah.
later on, we're going to come back to the more things change, the more they stay the same.
Yep. So then desktops were made, laptops were made. Everybody has desktops and laptops. Carrying them around. The phones. These are more powerful than the room of computers that I used to work on. Then the internet came. That was in 95, 94, 95, and shopping.
I want to put in a couple
Go.
intermediate steps. So
Intermediate-
you end up with computers that do things.
Yeah.
A computer did a thing.
Independently.
And for a long time, computers didn't talk to one another. Internet grew out of, you've heard of ARPANET, effort to get computers to talk to one another in really interesting and useful ways. Before that, though, you could set up a local area network.
Which we did.
We did, right? So you end up with computers that can talk to one another. And in any given office, in any given business, you would have their network. Pre-internet, the network didn't actually go out and connect to anything else. It was the local stuff. Then you end up with an internet that supports at least a few basic services, email being the very first that anybody cared about. So you end up, and it's important to remember that people who managed business computer systems had a local network that they needed to care about, and they needed to know which machines were connected to which other machines and how were they identified, and if there were multiple subnets, where were the routers. And we had network diagrams that were maps of the networks that we were managing. Then comes services outside our office, the internet, other stuff out there.
Well, the first thing was, of course, the web. You had websites starting to spring up. eBay was one of the actually first websites that would do selling and stuff. But then Amazon came, and they realized that they can't go down. So they bought hundreds and hundreds and hundreds of servers and made sure that for the 1 week before Christmas, that everybody was online buying from Amazon, they would respond quickly. For the other 51 weeks of the year, they had these hundreds and thousands of computers doing nothing because they didn't need them except for that 1 week. But it was important for that 1 week.
So they had them.
But for the 51 weeks, what are they doing?
Kind of mostly sitting idle.
So Amazon decided to do what they did way back in the 60s and sell pieces of time on their computers. This is the initial cloud.
And there were steps to get there. I was talking about offices with their own network. Early on, every office kept their network and all of their servers and their computers in the same building. There was a server room in the office. Eventually, that got to need specialized electrical support, specialized network access. And so they invented co-location centers out in the world, big warehouses that had really good cooling, because servers don't like living in the same kind of environment that people do. They like it cold, and they like the power uninterrupted, and they like their network access really, really fast. And at the time, all of that was really expensive to do in an office building. But you could rent space in a co-location center and put your server racks there. And a little further down the road, having your own servers in somebody's co-location center wasn't going to be nearly as cost effective as just renting theirs, because when you buy a server, then you've got to maintain it, and after a couple of 4 years, you've got to upgrade it, and it's just a whole lot easier to rent somebody else's servers. They'll buy it, and they'll sell you the use of it, and they'll keep the software upgraded, and after it's depreciated its value completely, they'll swap it out for a new one, and you just keep renting it. And then it wasn't even you get a server of your own that you can identify. Then it's you get some chunk of the compute power that somebody else has filled up a warehouse with. So the cloud now is just the logical next step of somebody else housing your compute power or housing compute power that you buy from them. And at this point, we're not even talking about servers anymore. When you go spin up a server in Amazon Web Services or in Google Cloud Provider or in Microsoft Azure, you're not creating a server that is a physical hardware platform. You are describing a quantity of compute power in terms of typically virtual vCPUs and an amount of memory and an amount of associated, not even necessarily attached, storage. And they have software that is going to cobble together a virtual machine that looks like this machine profile that you've given them. And it's going to consist of, you have no idea what hardware lives under that and supports it, what networking actually connects the bits and pieces, what software is managing that software-defined network, what flavors and layers of store, and none of that matters. That's what abstracting away from the physical does for you. It's, just the next step in abstraction. So when Jay asks how many servers does Amazon have, it's like, it's a trick question. Are you talking about how many pieces of hardware have they installed in racks? Hundreds of thousands, maybe millions.
So
how many VMs are running on those?
who knows?
It changes literally minute by minute.
So when you go out and want to create a cloud machine, there are certain minimum requirements that you need to know. What is the CPU that I want? How powerful do I want this thing? How much memory do I want? Do I want 2 gig? Do I want 200 gig? Cost more for 200 gig. How much disk space do I need? Depends on your application. What are you doing with your disk? Those are the minimums. The cloud stuff that exists today, when you create your virtual cloud machine, you can say, I want a Postgres database. I want a Microsoft SQL database. I want a Cockroach database. You can specify what database you want. I want Java Message Services service running. You can specify, I want my disk backed up weekly, daily, hourly. There's so many of these services that are built into the cloud now that you have no need to have your own computer, except to access that.
It's true. It's true. I mean, the only issue there is cost. And
Yes.
Cost is not just measured in dollars. I talk about trade-offs, about you conserve what's expensive and you pay for it with what you value less. Yes, you can translate almost everything into dollars, but a lot of those trade-offs are in time or in difficulty, in inconvenience. And the promise of the cloud, the original promise of the cloud, we talked about where it came from, was reducing the cost in terms of time and inconvenience to set up a server, right? It used to be, to set up a server, you ordered one from Dell or whomever, and you waited for it to get delivered. And when it got delivered, you racked it and you stacked it, and then you had to install the operating system, or at least modify the vanilla installation, because they're never exactly what you want. And then you needed to install the software on it. And this is something that your system administrator had to take a week to do. And that's just to get you the platform running so that you can use it for something. And then there's a cost of ownership that involves keeping it patched, keeping it up to date, doing maintenance, doing backups. The promise of the cloud was push that effort and activity off onto somebody else so that it's quick and easy. And over the years, it's become much quicker and much easier, so that now there's a web page at AWS that you log into and you say, I want a server, and you fill in the 7 boxes that describe it, and 15 minutes later, you have a server with all those services running using the latest and greatest vetted software out of the library.
But there still was a problem. You can hit a button and in 15 minutes, you have a server. What's it good for? It's a computer. It's a computer up in who knows where, but it's still just a computer. Even though it's virtual and it has everything you want, it's still just a computer. You need it to do something. So you have software that you want running on it. How hard is your software? How difficult will it be to take your software and put it onto that machine, configure it, get it to talk to the databases correctly, and get it to run, and expose all the ports and HTTPs and web services, websites to the real world? That's still a job. And guess what? People have made that easier. There's Docker and Kubernetes.
Yep.
I mean, see, these are things that are really, really new.
And some of them are already turning old.
And some of them are already turning old.
I mean, Kubernetes is less than 8 years old. It's a whole suite of software designed to make this task of standing up the computers you need according to a description somewhere of what they should look like and how they should interact with one another. Started out life as a collection of scripts and evolved into a big open source project and became the hottest thing on the block. And 3 years ago, it was the most important thing I could be learning to support my career. And today, everybody is doing what they can. Not everybody, but now it's not in decline. It's just not the hot thing anymore, and we'll see a significant drop off over time. But this is part of where DevOps comes in.
This is DevOps, where there's a thing called Docker. Who's heard of Docker? Yay, good. That's really good. You can encapsulate your entire project inside of a little Docker image, and then just throw it up into the cloud, and you're done.
Throw it anywhere that can run a Docker image.
Any place that can run a Docker image, boom. And then the project I work on, we have like 8. We create, I think, 8 every build we make. We create like 8 different Docker images and throw them up into different VMs, and they all talk to each other. It's a pretty big Kubernetes job to make them all link together and talk over the microservices. But once that task is done, all you have to do is hit a button. Boom, done. Never works 100% of the time.
No. By the way, building that, there's a whole other conversation we can have about tool chains. I mean, Jay's just described this exercise of we write code, and he didn't talk about it yet, but we run a whole bunch of tests against the code that gets written.
I want to talk about testing, but that's not going to happen.
Right. Before it can even become part of the product, it needs to know source code control and
code reviews,
and then turning this thing into a working program or set of programs, and then creating from those programs the collection of these Docker images, and then putting those Docker images somewhere that they can be tested and or used. And all of that is largely done by software. And it's done by software that every one of those pieces of software it's a piece of an ecosystem. Every one of them has a very specific job to do. And by the way, it competes for that job with 3 or 4 other pieces of software that's designed to do exactly that thing. You are coming back, right?
Yes.
Okay, good. Don't abandon me. So tool chains is a whole conversation learning about the ecosystem of software that exists to support the building of software, and the ecosystem of software components that support the world of setting up servers and networks and keeping them up to date and up and running. So yeah, that's DevOps, and that's something that Jay does a lot of, interacts with a lot. It's something that I depend on and try to interact with as little as possible. things that go on in the world that you will slam face first into as soon as you get a job. Wow, that's a really good question. Oh, see, this is where I depend on Jay. So Jay and I have been members of teams for all of our productive lives, and we've been on teams together. The teams we've been on together have been very small, tight knit, lots of informal communication, lots of 3 people sitting in a room, hashing out ideas, scribbling on whiteboards.
Jay Goldberg.
Going to our separate corners and doing stuff, coming back together and seeing, hey, did that work?
I work with people that do DevOps.
It generally doesn't look like that now. I suspect that the first job out of school you guys get, if you're going into
you can
software
communicate with Jay
development,
anytime. Jay Goldberg,
you're going to be put
LinkedIn.
on a team,
Right.
and you're going to spend months
Go
or
for it.
weeks or maybe a month or more onboarding, because you are being slotted into
As
a
intern or
pretty
as a
complex system. I work for Cockroach Labs. Cockroach Labs, when I joined it, was basically 100% remote. Partly because I joined it in the middle of COVID, but partly because they are a software company that builds a cloud-native product with people contributing code and support and sales efforts around the world. So it's like the perfect candidate to be a virtual company. It actually has offices in 4 different cities, and there are people that show up at offices.
There's SQL involved in stuff, but there's a lot of hibernate.
This whole company runs on software, and the software you use to communicate, the software you use to track projects, the software you use to manage code, the software you use for logging your time, the software you use for requesting time off. The amount of software that you're going to have to learn to use just to do your job. It's roughly, it's the onboarding process is roughly analogous to when you walked into the office and they showed you, here's the accounting office, here's where the timesheets are, and there's the bathroom over there. That was kind of orientation you got. Orientation in a modern company, no matter what you're doing, is
I gotta go back.
a whole lot more
I
complex
anticipate that
than
when we're
that.
done, we're gonna be questions.
Onboarding into a software company
Even we have ideas.
has lots and lots of moving parts, and it takes time to get those under your belt. And then onboarding onto a software team, you need to be prepared that the way they do things, the way they talk about things, there's whole methodologies that they will have in place that don't look like what you're used to, don't look like what you've been taught or learned how to do. So be prepared to be very surprised by how things are done. Yay. Okay.
You miss me?
You have no idea. No, the question was, what should they be prepared for joining a software team? And where I started with onboarding into a modern company and all the things that you're going to learn just to function in a new corporate environment, but specifically joining a software team, which I haven't done in years, and you manage people doing that all the time. Talk to them about joining a software team and what that's going to be like.
Okay. There are lots of tools that will be required. We try to get our IT department to pre-install them onto the new laptops when we have new onboards. That never happens. There's a lot of tools and a lot of services that you will need to learn. The tools will include mainly your IDE.
Yeah.
Let's all hear it for IDEs. Come on, woo! We didn't have them.
Yeah, no. It doesn't matter which one.
No, it doesn't matter which one.
The fact that there is any kind of integrated development environment in which your code can live and your lookup dictionaries live and the ability to compile, test, run, step,
refactor.
This is new in our, not lifetime, in our professional career.
Yes. So yay for IDEs. We used VI back in we had Notepad. That's what we had.
No, seriously, that was functional.
Really what we had.
The Unix equivalent of Notepad, which was.
So like, you can use a suggested IDE. You can use your own. Not recommended to use whatever you want because there's going to be a lot of expertise in the other more commonly used IDE. I used Eclipse for a long time at work until it stopped working. The new ones just don't work. So I moved over to IntelliJ. I said like we are a Java house, so IntelliJ is a very good Java development environment. So that's one of the main things. Your
source code control.
The source code control. Source code control has evolved over the years. I have been with PROS 19 years. Can you believe that? I have been there 19 years. We have used...
That beats my personal best by 7 years.
Yes. We have used half a dozen different source code control systems, but never had no source code control. You always have to have source code control. And I can't even tell you how many reasons why you want source code control.
Even when we were just 3 programmers on a team.
Yeah, we still had source code control.
We didn't just need source code control. We needed slightly more sophisticated source code control than was readily available at the time. And so the guy that we were working with beefed up the tools we were using.
Yeah. So where is the source code and downloading it onto your machine and getting it compiled? Sometimes that takes a couple days in my experience. So you get your IDE, you get access to the source code control. Do you want a tool, a UI tool to talk to your source code control? Optional. Most source code control systems have a command line. We use Git. I'm sure many of you have heard of Git. We do not use Git public. We bought our own. And we installed it on our servers. So we have our own copy of it running. Because our legal team wouldn't let us put our copyrighted software out in the world. Getting the product that you are assigned, you get put on a team. The team works on a product. Getting it to download the software, the source code onto your machine, get it to compile, and get it to run. Those are the #1 things that you will be doing. Most teams that I'm familiar with will have documentation of how to do that. If you're working on a team with microservices, you will be doing that per microservice. We have 1, 2, 3, 4, 5, maybe 7, depends on how you count, microservices. You can do them one at a time. If you get an assignment saying microservice A, we want you to download it, get it to compile, and fix a bug. Okay, you still need all those same tools. You still need your IDE. You still need your access to source code control. You still need to learn how to use the source code control. Even our version of Git's a little different than the one that's online. That's the technical side of the team. More esoteric side of a team is how many members, where are they located, how we interact, and when are the meetings. I'm hoping that most software companies do agile methodology, so we have a Scrum. We have ours at 9:30 in the morning. Every team's different. So how many team members, and how you communicate. Over the years, PROS has had many ways of communicating online between teams and between members of a team. Do not do that. When the first started to get instant messaging through computers, everybody downloaded every app. There was Yahoo messaging and ICQ messaging and
AOL
messaging. And so everybody had everything running. There will be a single messaging app that you will use for communication with your team. We happen to use Teams, but even that has been, we don't use Slack, but there's another one out there that
Okay.
Yammer.
Yeah.
Is
Yammer's been around.